Okie dokie. So today we're going to go ahead and talk about simple harmonic motion. First, what I want to talk about before we talk about simple harmonic motion is let's talk about an oscillation. So an oscillation is just any motion that repeats itself. So that could be someone running back and forth. So like a person running, to one person cone and then back to another cone and back to that cone and back and forth, just like that kind of thing. Or it could be like a pendulum oscillating back and forth. It could be like a wave oscillating up and down. So many things, so many oscillations in our everyday life. Now, simple harmonic motion is a specific type of oscillation. And simple harmonic motion is just motion that results from restoring force that is proportional to displacement. So that an example of that is like a spring force or like a simple pendulum that is oscillating back and forth due to gravity. Okay, so a couple things we're going to chat about. So make sure you have that written down. A couple things we're going to chat about for simple harmonic motion is period. So I want you to go ahead and take a guess what this definition is, write it down, and then check back into the video. And the period is just the time it takes to create one revolution. It takes, if I can spell, takes to make one revolution. Or you could say like one trip around or one cycle of motion, whatever it is. So since period is dealing with time, the units of period are going to be seconds per revolution. However, revolution doesn't necessarily have a unit, so you could just say that the units are just seconds too. You'll see either of those used for period. So now we'll oftentimes see this word frequency. So frequency is essentially the inverse of period. So it's the inverse of period. So, okay, inverse of period, let's guess what an equation is for that. Inverse of period is just 1 over period. So the equation for frequency is 1 over period. So let's think about what possible units are for frequency. So if it's 1 over period, it could be, let's see, 1 over seconds. Or I should say like inverse of period. So period is seconds per revolution. So we could say revolutions per second. Sometimes people won't write the revolutions as I did in the first example. So people might say seconds to the -1 or inverse. Let's see. Hertz is another one that people will oftentimes use, which is also just abbreviated as Hz. Now let's think a little bit more what frequency is. And it is the number of cycles of motion, so again like revolutions or cycles of motion per period of time, or per 1 second interval we'll oftentimes use. So number of revolutions an object completes in a unit of time. And we will oftentimes use the unit of time, as I said in the first one, it'll oftentimes be seconds. Okay, so we've talked a little bit about angular frequency this year. And we're going to talk about how that relates to regular frequency, F, which, again, the units are hertz. So we've talked about, in our unit on rotational motion, we've talked about angular velocity, which, again, the symbol for angular velocity is omega. In simple harmonic motion, we call angular velocity angular frequency. So these have the exact same symbol. Okay, keep that in mind. So we have, so we know angular velocity is, again, that is omega is like our change in theta over change in time. So let's say we're talking about something going around once. So if it goes around once, it's going to go through, so one rotation, that is going to go through 2 pi radians per whatever the period is, and so that will be t seconds. So the equation we're frequently going to use this year is omega is going to be 2 pi over period. So the angular frequency is 2 pi over period. If we wanted to put in, let's say, frequency in there, we know frequency is 1 over period. So if omega is 2 pi over t, this will be just, so this is like 2 pi times 1 over t, and 1 over t is just frequency, so 2 pi f. Honestly, like you could memorize this right here. I would just recommend, though, making sure you have the equations memorized. Omega, angular frequency or angular velocity, is 2 pi over period, and frequency equals 1 over period. Okay, we're going to go ahead and do a little solving. Okay, so we're going to do number 1 together, and then you all can try number 2 and 3 yourself. Okay, so for this first one, okay, the hummingbird flaps its wings 10 times every second. We want to find the frequency. I always love writing down the equation and what we're trying to find. So frequency is F. And again, frequency is 1 over period. Units for frequency, so that's going to be number of revolutions something makes per second. Okay, so let's see how many revolutions it makes. It makes 10 revolutions in every second. Every is like per every 1, so that's 1 second. Or if it was like for every 2 seconds, we'd put 2 seconds. So the frequency is just 10. You could say revs per second for your units. You could do 10 inverse seconds. Hertz is frequently used as the abbreviation or units for frequency. So any of those would be appropriate. Okay. So now let's go ahead and do B. For B, we want to find the period of time. So period is 1 over frequency. Actually, let's just go ahead and do it with equation first. So period is seconds per revolution. So again, for every 1 second, it is what? 10 revolutions. So the period is just going to be 0.1 seconds. Cool. You can also use your equation where frequency is 1 over period, or period that means is 1 over f. So 1 over, we found the frequency to be 10, and that will also get us 0.1 seconds. Cool. Should erase my little scribble mark. Sorry about that. Okay, let's go ahead and look at C. We want the angular frequency. Angular frequency is omega. The only equation, I know I just gave you 2 equations, but the equation I remember, angular frequency omega is going to be 2 pi over period. The period is 0.1 seconds, so this is like 2 pi over 0.1. Let's see, so 2 over 0.1, that's like 2 divided by 1/10, which is just going to be 20 pi radians per second. Okay, I'm going to go ahead and post the answers for 2 and 3. I would pause the video yourself right now, try them, and then check back in for the cool. There are the answers for number 2 and 3. Cool. We're going to chat a little bit now about graphing simple harmonic motion. Okay, so I want you to think now about how might we graph simple harmonic motion. Again, with simple harmonic motion, I think of like something oscillating back and forth. A wave is not necessarily simple harmonic motion, but that is an oscillation. We're going to go ahead and use sines and cosines. Any type of motion that repeats itself, sines and cosines are a great thing to use for graphing. Okay, a couple just general definitions. So what is the amplitude? That is going to be the max displacement from equilibrium. So if we have, let's say we have something oscillating, okay? So we have a graph, we have something oscillating back and forth, back and forth. Equilibrium is, I think, essentially like the x-axis. The amplitude is like the distance from equilibrium. So it is not the distance from the crest to the trough, it is half that distance, so the distance from equilibrium. Okay, so a couple things. The general equation of motion is going to be x of t, or y of t, whatever it is. You could say is a cosine, I'm going to find all these things in a second, omega t plus or minus b, or if it's a sine function, we'll say x of t equals a sine of omega t plus or minus b. Okay, those are our 2 things. So a couple things to define. A, as you probably guessed, just stands for amplitude. We will oftentimes want those units to be in meters. Okay, omega is, as we previously defined, that is angular velocity, or you could call it angular frequency. Either of those would be just fine. And again, the equation for angular frequency or angular velocity, when we're dealing with simple harmonic motion, is omega equals 2 pi over period. Okay, B is going to be and we're going to want, angular frequency or angular velocity, we're going to want the units to be radians per second. B, again, is a phase constant. So if the max or min of the graph is not at 0, we will have one of these. Okay, while if the max or min, so like in the graph I drew above, the max is at, x or t equals 0, whatever that is. So if I say this is x and this is t, so we do not have a phase constant. But if it's like something like, let's say, where it's, let's say the max is here, this would have a phase constant. So if it's positive, the graph will shift left, and if it is a negative, the graph will shift right. Cool. Most of the time in this class we won't deal with phase constants, but it's good to know about them anyways. You'll see them again in the future in your life. Okay, so now let's go ahead and find an equation of motion for each graph. So first thing I do, I go ahead and write down some information about the graph below. So for this, okay, there is, so the amplitude, let's go ahead and figure out what the amplitude is. I'll go ahead and do it in a different color just to mix it up. So the amplitude is, again, the distance from equilibrium. That is just going to be 3 meters in this case. Period. That is the time for one complete cycle. So it starts here. Next time it is at a high point. Oh, that's just 1 second. Huh, nifty. Period is 1 second. Okay. Let's think about what type of graph this is. So this is going to be a cosine function because when the t equals 0, it is at a maximum. So we know this is a cosine graph. Again, if it's at this, at t equals 0, if the position is at 0, then it would be a sine graph. The max or min is at the initial starting position, so we know we do not need a phase constant. So we're going to essentially use as our equation of motion, x of t is a cosine omega t. So now we just essentially need to plug things in. The variables in this case are x and t. So we know a is going to be 3. Cosine, we need to plug in omega. I want you to think about what omega is. T, again, is our variable. T does not stand for the period. T in this graph, like that's varying. We're looking at a bunch of different times in the simple harmonic motion. So omega, again, is 2 pi over t. So that is going to be 2 pi. The period in this case is just 1. So that's just going to be 2 pi. So we can go ahead and I should include my units. That's radians per second. So 2 pi in there. Cool. And so that is just our equation of motion. X of t equals 3 cosine of 2 pi t. Great. Thanks so much for watching. And I'll go ahead and just leave you with 2 bonus ones you're welcome to practice on your own. I'm not going to explain them here, but you can check for the answers. Right. But again, try these 2 problems yourself, finding the equation of motion for these 2 graphs, and then check back in on the video. Cool. And here are the answers to 2 more fun little problems. Try, and again, I always just list the amplitude period and then find omega first. Choose if it's going to be a cosine or sine function. And there you go.